Euler-Cauchy equation. Okay, so we have a new type of equation which looks like this. X squared y double prime plus ax y prime plus b times y is 0. Okay? Alright. So this is different from the previous type of equation, which is constant coefficient, right? So we have x in the coefficient function. Okay? But in that form, x squared, that square has to be the same as, the highest order of the derivative, and the next, lower x. So that form, only that form, that's Euler-Cauchy equation, and we're going to solve it, right? So what are you going to do when you see a new type of equation, new type of differential equation? Try, that's right. That's good. All right, let's try, right? E to the lambda x. Okay? And y prime is lambda times e to the lambda x. That's how you do, okay? All right. And we plug it in, right? We substitute in. And then x square, lambda square, e to the lambda x. Let me just write that. Plus a x lambda plus b e to the lambda x is 0. Correct? All right, then this one has to be 0. Do you see that? Do you think you can get lambda out of that? How's that? We can solve it, right? Because x is another variable, right? We cannot get, roots for the two variables at the same time, right? So in this substitution, no, we cannot make it, right? So we need to get a new candidate function that satisfies this equation, right? Fortunately, Euler-Cauchy made such a good suggestion, which is y is x to the m. Okay, they found this one doesn't work, right? And they made a lot of thinking, right? And then they eventually got this, right? And let's see how it works. So y prime is m times x to the m minus 1. Y double prime is m times m minus 1, x to the m minus 2. Okay? And we substitute it in, right? So x squared m times m minus 1, x to the m minus 2, plus ax mx m minus 1, plus bx to the m, right? And this is equal to 0. And you have to multiply x to the square, to here, by having m minus 1 x to the m plus a m x to the m plus b x to the m. Okay? And so you will be able to get m minus 1 plus am plus b, which has to be 0. Okay, so you have a different type of characteristic equation, and that is characteristic equation. And you need one more steps, which is plus a minus 1m plus b is 0. That's characteristic equation. Okay, the only thing is, this is a minus 1 due to the fact that it's, this x is included in the equation. It's a slightly different form, right? Our previous, result was lambda squared plus a lambda plus b is 0 compared to that. Okay? So we have a different characteristic equation. And our root of that characteristic equation is, so m is 1 minus a plus minus square root of 1 minus a square minus b divided by 2. That's our, okay? So we have three cases. M1, the inside of the square root is greater than 0. Then we have two different numbers, roots, okay? Then our, y is c1 x to the m1, right, plus c2 x to the m2, which is, quite reasonable case, right? Okay? And secondly, if m1 and m2 is 0, I mean, the inside of the square root is 0, okay, then we have a same, roots, real numbers. So secondly, we have double roots, one real double root, right? So we gotta need to what? So we have, so we need to do the reduction of order, right? Oops. So reduction of order, which is our case m1 is 1/2 times 1 minus a, right? Then we have only this term left, right? So we need to use the formula, right? So x to the 1 minus a over 2. That's our y1, right? Only y1. So our, u is the big U dx, do you remember? And where big U is is y1 square, the formula, okay? P dx. Okay, that was the formula, reduction formula. And our P was a over x. Right? So our big U is 1 over x to the 1 minus a times e to the minus a over x dx. Okay, then that's a minus 1 times e to the minus a ln x. Okay? And then, which is x to the a minus 1 times x to the minus a. Okay, so that's 1 over x. That's big U. The separable first order variable is big U, right? And we need, small u, ln x. Okay, and y2 is u times y1, which is ln x times y1. Okay, so our y for the second case is c1 times c2 ln x, x to the m, m1 or whatever, one root. Okay, so example 4. This is the problem of using Euler-Cauchy equation into electric potential. Potential analysis in a capacitor. Spherical capacitor, okay? Right, this complicated process or phenomenon in the nature can be modeled using the mathematical equation. That's what, this purpose of this example, right? So from the experiment, they found this. Okay, so V is the potential, voltage. Actually, it's voltage, electric potential. Okay, and R is the distance or the radius of the the capacitor ball sphere. Okay? So this equation, somebody who really knows, about the capacitor made from the experiment or whatever, they made this equation. Okay? So usually they made it for you, or even you can make it, right? Right? So that's what it is. It's given. Mostly it's given, okay? All right. But then, it looks like Euler-Cauchy, right? But except we should have, r to the 2, right? To have a exact Euler style, right? But it's quite kind of similar. And let's see if it works, okay? And we can find some principle or rule to really make it work, all right? By the way, we have a 2 boundary condition. One is R1 is 5 centimeters, and our R2 is 10 centimeter. Okay, and at R1, the voltage is 110 volt. Okay, and on R2, V2, which is 0 volt. Okay, and that's the convention. So the plus charge, we say positive voltage, okay? A negative charge, we say is 0 volt, okay? And then, let's see. So our Y, sorry, not Y, we are using V. V is R to the M. Right? Our dependent variable is V now, right? And independent variable is R, okay? The radius. So our Y has to be V, our X has to be R, and our, characteristic equation variable is M. Okay? You get it? All right, so V prime is M times R to the M minus 1. V double prime is M minus 1, R to the M minus 2. We plug it in, right? Then R times M minus 1, R to the M minus 2, plus 2 times M, R to the M minus 1 is 0. Okay? So it's M times M minus 1, R to the M minus 1, plus 2 M times R to the M minus 1. Okay, so our M minus 1 plus 2 is 0. So M square is 2M. So plus M is 0. Okay? So we were able to get a, characteristic equation on this case. Right? Okay? So our M from the root, M is 0 and minus 1. 2 real double roots. Okay? And our, solution is V is function of R, which is C1 plus C2 over R. Okay? And with the, to determine C1 and C2, you could put 2 boundary conditions, right? We have 2 unknowns. We need 2 conditions, right? And we have 2 conditions here. That's a boundary condition. That's a slightly different from initial condition, but that's a boundary condition. And you're going to learn the boundary condition in later course, okay? So, anyway, V5 is, we use the boundary condition, right, to determine the C1 and C2, right? V of 10 is C1 plus C2 over 10, which is 0. Okay? And by using, this, C1 is minus 110, C2 is 1100. Okay? And you plug it in, then we're going to get our particular solution, Vp, which is minus 110 plus 1100 over R. Okay? That's actually voltage. That's V, the unit.